Good morning or afternoon, everyone. Welcome to my sharing today. My name is Chang Li, and the topic I'm going to dive deep into is the M42 framework, with a full technical breakdown of its pre-retrieval enhancement technology. RAG systems have become the mainstream infrastructure for enterprise AI Q&A and knowledge retrieval, yet many teams still struggle with low retrieval relevance, ambiguous user queries, and severe LM hallucinations. The M42 framework we built addresses these pain points systematically, and the core breakthrough lies in its pre-retrieval module. Over the next 15 minutes, I will walk you through the full architecture, core logic, underlying engines, key algorithms, and practical business value of this technology. Let's jump into our agenda first. Here is our complete agenda, divided into 6 core sections. First, we will overview the 6-stage full RAG pipeline of M42 to help you grasp the overall positioning of pre-retrieval enhancement. Second, we will clarify the irreplaceable core status of pre-retrieval within the entire M42 workflow. Third, we'll unpack the underlying StateMachine orchestration engine that supports all pre-retrieval logic. Fourth, we will conduct an in-depth analysis of input augmentation modules, focusing on 3 mainstream NER implementation solutions. Fifth, we'll introduce 6 core query augmentation rewriting algorithms optimized for retrieval performance. Finally, we will wrap up with a comprehensive summary of the technical and business value brought by the M42 pre-retrieval system. Let's start with the full M42 RAG architecture. The M42 framework reconstructs the traditional RAG pipeline and splits it into 6 mutually complementary, parallel optimization stages. Each stage is empowered by self-developed exclusive core algorithms, forming a closed-loop technological system that comprehensively lifts retrieval accuracy and final generation quality. Let me go through each stage one by one. First, pre-retrieval enhancement. This is the entry gate of the whole pipeline. It optimizes raw input quality and parses ambiguous user intent. We've developed 12 dedicated core algorithms here to polish unrefined queries, extract key entities, and decompose complex multi-layer questions, laying a solid high-quality foundation for downstream retrieval. Second, retriever enhancement. This stage focuses on boosting knowledge recall capacity via hybrid search modes. 6 proprietary algorithms support dense embedding matching, sparse keyword inverted indexing, and generative retrieval, covering heterogeneous multi-source enterprise knowledge bases. Third, retrieval strategy enhancement. It targets multi-turn conversational interaction scenarios. 11 algorithms enable adaptive knowledge routing, dynamic query rewriting, and memory-augmented retrieval paths to maintain dialogue consistency. Fourth, index enhancement. We optimize the underlying knowledge-based storage architecture. For algorithms, refine text chunking logic, index partitioning rules, and metadata lifecycle management, cutting query access latency significantly. Fifth, post-retrieval enhancement. Before feeding retrieved documents into LLMs, this module refines raw search outputs. 3 algorithms handle relevance re-ranking, duplicate content deduplication, and context compression, reducing LLM reasoning overhead while retaining valid information. Sixth, LLM enhancement. The final stage upgrades model reasoning capability. 3 core algorithms integrate chain of thought prompting, self-consistency verification, and tool-augmented generation to deliver precise, grounded answers. Among all 6 stages, pre-retrieval enhancement acts as the source of quality control for the entire pipeline, which is why we prioritize it as our core research focus today. Now, let's talk about the core positioning of pre-retrieval in M42. We define pre-retrieval as the front-end brain of the entire M42 RAG pipeline. It serves as the critical bridge between messy, unstructured user intent and high-efficiency downstream retrieval. Its core mission is converting vague, incomplete natural language inputs into standardized, semantically rich structured queries, which fundamentally improves the accuracy of document retrieval and the reliability of LLM generation. Its working flow consists of three key layers. First layer, raw input capture. The system directly ingests unprocessed user natural language queries. These raw inputs often contain colloquial slang, logical ambiguity, missing background context, and fragmented expressions, which cannot be directly used for vector search. Second layer, core enhancement and rewriting hub. This is the semantic transformation center of pre-retrieval. It completes three major types of semantic optimization work: input augmentation and query augmentation. For input augmentation, we carry out deep semantic parsing. NER entity extraction locks critical factual anchors, such as names, geographic locations, organizations, and professional technical terms. Knowledge graph mapping builds associative semantic networks to resolve ambiguous references and supplement external correlated knowledge. Intent normalization converts casual vague statements into unified standard intent labels for consistent batch processing. For query augmentation, we deploy multiple expression optimization strategies. Paradigm-driven rewriting uses our QRAG and DMQR to generate diverse query variants matching vector retrieval patterns. Hypothetical document embedding, or HYDE, generates plausible simulated answer texts to retrieve semantically matching real knowledge documents. Multi-perspective expansion leverages QOQA and back translation to broaden search coverage and avoid one-sided retrieval bias. Third layer, downstream retrieval and generation. All polished, augmented structured queries drive precise vector database recall, multi-document re-ranking, and finally guide LLMs to produce fully grounded, context-aware response content. Without this pre-processing layer, downstream retrieval will face severe missing recall and irrelevant noise issues. Next, let's look at the underlying technical support: our self-developed generic StateMachine orchestration engine. All pre-retrieval steps like query rewriting and NER extraction are encapsulated into independent, reusable state units. This standardized state transition mechanism solves tight coupling pain points in complex multi-step pre-processing workflows, making the whole pipeline efficient, controllable, and fully testable. It has three standout design advantages. First, explicit, transparent orchestration. Every processing step is a visible state unit, with execution sequence clearly defined during initialization. There's no black box logic hidden in the workflow, so engineers can trace every execution step for fast debugging and fault location. Second, unified context carrier object. A single shared context data stream transports raw queries, rewritten query texts, extracted NER entities, and full multi-turn conversation history across all state nodes. It completely eliminates data silos and ensures seamless information circulation throughout the full link. Third, modular and highly extensible. All processing nodes are interchangeable and combinable. When we need to add new query rewriting strategies or domain-specific NER algorithms, we only create a new state module, with zero refactoring work on the core StateMachine engine, greatly lowering system iteration and maintenance costs. Let me walk you through the full context-driven data flow. First, initial input injection. Raw user query is written into the shared context object to trigger the StateMachine workflow. Second, semantic enhancement stage. Multiple state modules run to generate rewritten query variants and extract NER entities, injecting structured semantic features into context. Third, dialogue history fusion. Multi-turn chat history is merged into context to realize long-term context awareness and consistent dialogue logic. Fourth, retrieval-ready output. The fully enriched context carries complete semantic clues and entity labels to trigger accurate knowledge base recall, document re-ranking, and final response generation. Now we move to the core input augmentation module, named Entity Recognition, or NER. The core goal of NER is extracting critical key elements from unstructured text, converting plain language into structured, machine-processable data to support all downstream intelligent logic. Its core design positioning has four dimensions. First, core intent, entity structuring. Accurately identify and extract high-value entities, including proper names, locations, organizations, and domain technical terms, translating free text into standardized machine-readable entity data for AI comprehension. Second, plug-and-play architecture. We define a unified standard NER service interface, with NER service as the default high-precision implementation. Powered by conditional bean injection, developers can seamlessly swap in lightweight domain-specific NER models for medical, legal, or financial scenarios without rewriting core business code. Third, clear performance trade-offs. LLM-driven NER delivers outstanding cross-domain generalization with no task-specific fine-tuning required, but it comes with slightly higher inference latency and computing cost, and may struggle with ambiguous entity boundary detection in extreme edge cases. Lightweight local NER runs faster, with lower cost, but lacks generalization capacity. Fourth, wide application scenarios. NER serves as the foundation for numerous deep semantic businesses, enterprise knowledge graph auto-construction, personalized intelligent recommendation systems, financial news event extraction, and clinical medical record parsing in the healthcare industry. We have 3 mature, switchable NER implementations in M42, which I will introduce one by one. First solution, traditional local rule-based NER. You can see the sample entity tagging case on screen. The text about pre-database marks business, persona, date, organization type, and name entities with distinct color labels, which is the typical output of this pipeline. Its workflow relies on 3 parallel local recognition branches. First, NLP toolkits such as HAMP and Stanford NLP complete tokenization and part-of-speech tagging for preliminary entity extraction. Second, domain entity dictionary matching loads custom glossaries and applies maximum forward or backward matching rules. Third, regular expression pattern libraries run customized rule matching for domain-specific entity formats. After parallel extraction, a post-processing module merges and deduplicates all candidate entities, then assembles standardized NER object lists as final output. Let's summarize its pros and applicable scenarios. Advantages: it runs fully locally, with no external cloud dependencies, requires minimal computing resources, and avoids network transmission latency. It fully meets strict on-premise data privacy requirements. Ideal use cases: legacy enterprise systems, edge computing deployment, and simple structured domain texts, where heavy deep learning models are redundant. Core takeaway: this rule-based solution balances ultra-low latency and data autonomy, making it a reliable choice for offline and privacy-sensitive production environments. Second implementation, BERT Transformer Sequence Labeling NER. The screen displays the standard stacked multi-layer transformer architecture of BERT, the foundation of this solution. Its complete execution pipeline has 4 phases. First, tokenizer preprocessing. Raw text passes through BERT word piece tokenization, adds special token markers, applies fixed length padding and truncation, and generates attention masks. Second, BERT encoding layer. Multi-layer bidirectional self-attention transformer blocks calculate deep contextual embedding vectors for every token. Third, NER prediction head, a fully connected layer followed by softmax or CRF layer, predicts entity labels under the bio or BIOS tagging system. Fourth, post-processing decoding. The model selects labels with maximum probability, applies bio-boundary rules, and maps segmented tokens back to original text to output complete entity objects. Core strengths of BERT NER. It captures full sentence bidirectional context, resolving semantic ambiguity that traditional static word embeddings cannot handle. It achieves state-of-the-art precision on well-labeled domain datasets and supports targeted fine-tuning for vertical industries including healthcare, finance, and law with limited annotated data. Its limitations are also clear. It demands labeled training data for fine-tuning and brings higher inference latency and resource consumption compared with lightweight rule-based pipelines. Third, an artificial default solution, prompt-engineered LLM-driven NER. The template prompting example on screen illustrates its core logic. The model enumerates every text span in the sentence, fills the span into a fixed prompt template with a mask placeholder, and calls the large language model to predict the entity category for each span. The core power of this approach lies in prompt engineering. We design high-precision structured prompts to guide LLMs to extract entities directly from raw text, returning standardized JSON-formatted results that can be connected to APIs and databases without extra conversion. 3 unparalleled advantages. First, zero-shot cross-domain flexibility. It adapts instantly to new industries or custom entity types without any fine-tuning or labeled training data. Second, standardized structured JSON output. All extraction results follow unified schema definitions for seamless integration with downstream systems. Third, dynamic prompt control. Adjust extraction logic in real time by updating prompt templates with zero model retraining overhead. Now let's look at its end-to-end workflow. First, input text is injected into the LLM-NER service. Second, the system loads predefined JSON prompt templates and builds complete request context. Third, the unified chat model delegator initiates LLM inference calls. Fourth, the service verifies whether model response is valid JSON with complete entity fields. Fifth, if verification passes, the system parses entity text, type and position information, assembles standardized NER objects, and returns them. If invalid, it returns empty entity lists to avoid pipeline breakdown. For M42's general enterprise scenarios, LLM-driven NER delivers the best balance of flexibility, development efficiency, and cross-domain adaptability, so we set it as the default built-in NER module.